In addition to the Gini index, another popular measure of diversity is entropy. The formula for computing the entropy value is negative sum of the product of class proportion and the base 2 log of class proportion. In other words, to compute entropy, you first find out the proportion of cases that belong to each class, multiply the proportion by the base 2 log of proportion, sum up all the products, and multiply the sum by -1. I also want to point out that technically you can use any number as the base for log. You can even use the mathematical constant e for natural log in the computation of entropy. The reason why we use the base 2 log is because we are focusing mostly on binary outcome problems in this course, and the base 2 log gives us the number 1 to indicate a completely impure subset using entropy, which is easier to remember. If you are a little rusty on logarithm calculation, please search the web and go over a quick tutorial on that topic. I have also included a link to a logarithm calculator online to make it easy for you to perform logarithm calculation. You can also use the log function in Excel to achieve the same results. So what is the range for entropy? Suppose we have two classes, class 1 and class 0. If all cases in the subset belong to class 1 and none belongs to class 0, then the proportion for the class 1 cases is 100%, and the proportion for the class 0 cases is 0%. So we compute negative 100% multiplied by the base 2 log of 100%, or 1, plus 0% multiplied by the base 2 log of 0%. And the resulting entropy value is going to be 0, as the log of 1 with any base is going to be 0, and the 0 times anything is 0. So for a completely pure subset, the entropy value would be 0. Then what about the opposite, or completely impure subset, where half of the cases belong to one class, while the other half belong to the other class? So the proportion of the two cases will be 50% and 50% in this case. And the entropy value would be negative 50% multiplied by base 2 log of 50% plus 50% times the base 2 log of 50%. Because 50% is the same as 1/2, and the base 2 log of 1/2 is going to be -1. So that gives us negative 0.5 plus negative 0.5, which is +1. So for a completely impure subset in a binary outcome case, the entropy value is 1. So as you can see, for a binary outcome problem, the entropy value would range from 0 to 1, with 0 indicating a completely pure subset and 1 indicating a completely impure subset. The closer the entropy is to 0, the purer the subset is, and similarly, the closer the entropy is to 1, the less pure the subset is. Please feel free to test a few different class distributions on your own. For example, a 90% and 10% split, or 70% and 30% split to see if this is true. Again, the entropy range is different for more than two classes, and the values of entropy do not increase or decrease proportionately to the degree of purity. Now let's look at our example again. But this time, instead of using the Gini index, let's compute the entropy value for splitting the case according to age equal to 49. We will start by computing entropy for the original 20 cases. The class distribution for the original 20 cases are 5 out of 20 for class 1 and 15 out of 20 for class 0. So the entropy value for the dataset is computed to be 0.8113. As it is quite close to 1, it suggests that the original dataset is not very pure. Partitioning the cases using age equal to 49 creates two subsets. The subset on the left, where the customer's ages are less than 49, has the class distribution of 2 out of 16 for class 1 and 14 out of 16 for class 0. So the entropy value is 0.5436, suggesting a purer subset. The subset on the right, where the customer's ages are more or equal to 49, has the class distribution of 3 out of 4 for class 1 and 1 out of 4 for class 0. So the entropy value is 0.8113. Again, using the weighted average approach discussed earlier, the combined entropy value for the split at age equal to 49 is 0.5971. Compared to the original entropy of 0.8113, the split is able to improve the purity of the resulting subsets. Please feel free to pause the video and compute the entropy values to verify. Again, with 34 candidate split points, the split search algorithm will compute the entropy values for all potential splits and select the one that produces the lowest entropy value as the first split or the root node for the classification tree. The final purity measure that we are going to discuss is the chi-squared test, also called chi-squared test of independence. As the chi-squared test is more interesting to look at using a dataset with more cases, we are going to use a different example than the one we used before. In our example, we have a total of 1,500 cases of personal loan customers, half of which have defaulted on the loan, and half of which did not default on the loan. We want to see if the ownership of a home is a good predictor for predicting whether a customer is going to default on a loan or not. In other words, we want to see if splitting the cases based on home ownership would create pure subsets. The data are summarized using the contingency table labeled observed. For example, among the 1,500 customers, 300 homeowners defaulted on the loan, whereas 450 renters defaulted on the loan. 550 homeowners did not default on the loan, whereas 200 renters did not default on the loan. One thing that I would like you to pay attention to is the total number of people who defaulted and did not default. Both numbers are 750, making the overall default rate 50%. Chi-squared test is a statistical test used to determine whether there is a statistically significant difference between the expected frequencies and the observed frequencies in one or more categories of a contingency table. Okay, let's try to understand this. If you take a look at the contingency table labeled the expected, you will notice that half of the 850 homeowners defaulted and half did not default, and half of the 650 renters defaulted and half did not default. This essentially suggests that home ownership is not a good predictor of whether someone is going to default on a loan, because no matter if a person is a homeowner or not, the chance of default or not default is always 50%, which is the overall default rate we computed earlier. The expected contingency table shows that if home ownership is not a good predictor of loan default, then we would expect both homeowners and the renters to have the same overall default rate, which is 50%. So 50% of the owners and the renters would default, and the 50% of the owners and the renters would not default. As you can see, to construct the expected contingency table, you simply apply the overall class distribution to both partitions of the cases, suggesting that the split makes no difference in improving the purity of the dataset. The question is this consistent with what we observed in the dataset? Or is the frequency values in the expected contingency table significantly different from the frequency values in the observed contingency table? If they are the same or statistically the same, then it means that home ownership is not a good split, as it does not create purer subsets. The purity of the resulting subsets is simply the same as before the split. Chi-squared test allows us to test whether the values in two contingency tables are statistically different from each other. As the expected contingency table represents an impure subset, the more different the observed contingency table is from the expected table, the purer the resulting subsets are, and the better the split. The formula for computing the chi-square statistic is displayed in this slide. To compute the chi-square statistic, you compute the squared differences between the frequency values in the observed table and the expected table, divided by the frequency values in the expected table. The sum of the values is the chi-square statistic. I will show you how to perform the calculation and interpret the results in the next slide. Now let's compute the chi-square statistic for this problem. We compare the frequency values in the observed contingency table to their respective values in the expected contingency table. For example, the number of homeowners who default in the observed contingency table is 300, and the number of homeowners who default in the expected contingency table is 425. Therefore, we squared difference between 300 and 425 and then divided the result by what's seen in the expected contingency table, which is 425. After computing that value for all four frequency values, we sum up the values to get the chi-square statistic, which is 169.4. So, what does the value of 169.4 mean? We can use the p-value of the chi-square statistic to find out if the frequency values in the observed table are statistically different from those in the expected table. There is an easy way to find out the p-value using Excel. The Excel function chi-distribution returns the right-tailed probability of the chi-squared distribution. The function requires two parameters. One is the chi-square statistic, which is 169.4 in this case, and the other is the degree of freedom. The degree of freedom is computed as the number of rows minus 1 multiplied by the number of columns minus 1. In this case, there are 2 rows in the contingency table and 2 columns in the contingency table, so the degree of freedom is 1. By entering the formula chi-distribution 169.4, 1 in Excel, it returns the p-value for the chi-square test. In this case, the p-value returned is a very small number. It is 1.00049 e negative 38. We usually use p-value less than 0.05 as the criterion for statistical significance. Therefore, the very small p-value shows that the frequency values in the observed table is significantly different from those of the expected table. This means that home ownership is a predictor that creates 2 different groups in terms of loan default. Therefore, it is a split that will lead to purer subsets. To compare which candidate split point is the best split point or the one for the root node, the split search algorithm compares the p-values for all the split points and select the one with the smallest p-value, or the split that creates an observed contingency table that is most significantly different from the expected contingency table. This is a summary of how chi-squared test works to identify the best split point in a decision tree. In the next few slides, I will show you visually how computer software would use impurity measures to grow a decision tree.